Hey, Cal, I am home today with a sick kiddo, but I still want to make sure you got the notes after your quiz. So we will be working on Riemann's sums, which is 5.3 on page 155 in your notes. And then it skips a little bit when we get to definite derivatives. But if you would go ahead and open there, and I will put up my camera for notes. Okay. So we're looking at Riemann sums, and Riemann sums help us start kind of looking at what an area under a curve looks like. So if our curve looked like this, we could pretty easily find what the area under it was. We've got a triangle with a height of 2 and a base of 1. So we know the area of a triangle is 1/2 base times height. 1/2 of 2 times 1 is 1. Then we've got a square that's 2 by 2. That gives us an area of 4. We've got a trapezoid, so we're going to do base 1, which is 1, base 2, which is 2, that's 3, divided by 2 times, this would be our height across the bottom here, which is 1, so 3/2. We've got another square that's 1 by 1, and then we've got a quarter circle, so with a radius of 1, 1/4 pi would be our area, and we'd add all these up and we'd find the area under this curve. Okay, but we don't always have graphs that are nice like that, so we can use something called a Riemann sum, which stacks rectangles commonly. We can also do it with trapezoids, and we'll look at that in a little bit. Stacks rectangles under the curve, and there's a left Riemann sum and a right Riemann sum. So our left Riemann sum literally means that the left endpoint of our rectangle is what's touching the graph. Okay, so we see on all of these rectangles, the upper left point is what is touching our graph. In a right Riemann sum, the right upper point is what's touching the graph. Okay, so the upper right point of our rectangle touches each graph. If we're looking at this, we see that this graph is increasing. Okay, if our function is increasing, the left Riemann sum is an underestimate. And we notice that because there are areas under the curve that have been left out. Okay, these little triangles sitting under there. The right Riemann sum is an overestimate. We have parts of our rectangles that are over top of the curve. Okay, so we're overestimating. If, however, our function is decreasing, then the left Riemann sum becomes an overestimate and the right becomes an underestimate. Okay. Now, to get better estimates, we're going to use more and more rectangles, which means they're going to get narrower and narrower. So this base across the bottom here, or this length is going to get shorter so that we have more and more rectangles. And the idea is that if we have more and more rectangles, we're exacting the area a little bit more. This is a truly bad example. We would like our rectangles to all be of the same width, like what we see over here. This is bad, okay? So when we're looking at each rectangle, the height of our rectangle is going to be our function f of x. And then across the bottom, that base is going to be delta x, that change in x. And that change in x should be constant across all the rectangles. And if we took all of the rectangles under a curve from f of x of 1 delta x plus f of x of 2 delta x all the way to f of x of n times delta x, because we multiply them for our area, we would sum them all up, we'd get this nice summation. And our approximation will be as the limit as n goes to infinity of the summation of f of xi times delta x, because this delta x is getting really, really small as we add more and more rectangles to it. Okay. We're not going to mess around with this too much, because what we can do, this is the limit definition of an integral. So we had the limit definition of a derivative. This is our limit definition of an integral. Okay. So to get some practice, we're going to use a left and right Riemann sum to approximate the area under this curve. negative x squared plus 2 from 0 to 1 using 4 intervals. Okay, so I'm going from 0 to 1 over 4 intervals. That means each interval is going to be a quarter. So I'm going to go ahead and mark out. This is 1/4, 1/2, 3/4. And then we get to 1. Same thing over here. Okay. Notice this function is decreasing. So our left Riemann sum is going to be an overestimate this time. And our right Riemann sum will be an underestimate. Okay. And I'm going to go ahead and draw my boxes so that the leftmost point on my box touches the graph. So you'll notice my rectangles here hang out just a little bit over the graph. But again, I want my left endpoint to be what's touching my graph. Okay. So if we want to find our area, we're going to say our first rectangle starts at f of 0 and goes to 1/4. So delta x is that width across the bottom that we said is a quarter of the way. So my first height is f of 0 times 0.25. My second height, my second left endpoint, is at f of 1/4 times 0.25. My third left endpoint is at f of 1/2 times 0.25. And my fourth endpoint is at f of 3/4 times 0.25. Okay. We're plugging in to our original function, which they gave us. Y is negative x squared plus 2. So we can use our calculator for this part. You can get 2 times 0.25, 1.9375 times 0.25, 1.75 times 0.25, and 1.4375 times 0.25 for an area that is approximately 1.78125. Okay, and again, we know that's an overestimate. So we're going to compare it against our right Riemann sum. For our right Riemann sum, remember we want the rightmost endpoint of the rectangle to touch the graph. And you'll notice we start to get a little bit of an underestimate. And again, I apologize, these bars are not exactly spaced where I want them, but my calculation, since I'm just plugging in, will be. So this time, when I'm looking at that first endpoint that I'm looking at, it doesn't start at f of 0. Okay, my first endpoint is at f of 1/4. I have the same width of 0.25. That did not change. My second endpoint is at 1/2. My third endpoint is at 3/4. My fourth endpoint is at 1. Okay. And each one of those is going to be multiplied by 0.25. So if you'd rather write it as 0.25 times all of, f of 1/4 plus f of 1/2 plus f of 3/4 plus f of 1, we can. Some of these calculations we already have. We know f of 1/4 is 1.9375. F of 1/2 is 1.75. F of 3/4 is 1.4375. F of 1 is 1, giving us a total area of 1.53125. Okay, so this is our underestimate, this is our overestimate. We would expect the area to be somewhere in the middle there, 1.6-ish. It just kind of depends. These are very, very close together. Again, I used a really small delta X though. That is not always the case. Okay, if we're looking at this next one, they don't give us a graph to go off of. They don't even give us the function that f of t is. So we just have to use what's in the table. Okay. We're going to do a left and a right Riemann sum. Okay. We notice our function is increasing from our y values. So our left estimate should be an underestimate, our right should be an overestimate. Okay. Remember, for our left Riemann sum in this picture, we picked the left endpoints. And even though we stopped at 1, we didn't pick it because that wasn't a left endpoint. Okay. Versus in this one, we didn't pick 0 because that was not a right endpoint, but we did pick 1 because that was a right endpoint. So same thing applies here. We're going to start by picking our left endpoints, which means we're going to leave out f of 8. Okay. But for our right endpoint, we're going to leave out f of 0. So let's try our left one first. So we have f of 0. The jump between 0 and 2 is 2. Then we'll take our next one, f of 2. The jump between it and 5 is 3. We don't love when this happens because we have rectangles of different sizes, but we work with what we have with this table. I'm sorry, that should be f of 5 times a jump of 2. And then f of 7 with a jump of 1. Okay, we're given these values. And we have an area that is approximately 59 as a left estimate. For our right estimate, we're going to work from the right backwards, or you can leave off f of 0. I'll start by taking my rightmost endpoint, which is f of 8, to leap back to 7, that's a 1. F of 7 with a leap of 2. F of 5, going backwards with a leap of 3. F of 2 with a leap of 2. Okay. And again, we're leaving off f of 0 because that's our leftmost point. Again, we are given the numbers for these. We have an area of approximately 112. But notice these are not close at all. And we get that one is an underestimate, one is an overestimate, but there is no, it's not like these where we're, tenths of a point off. These are far away from each other. And part of that has to deal with the fact that we're not taking the same step sizes between rectangles. Okay, our rectangles are not the same widths. If we had rectangles of the same width, we could probably get a little bit of a better approximation with stuff more close to each other. Now, rectangles are not the only way to do approximations. We also have midpoint and trapezoidal sums. Okay, so our midpoint sum still uses rectangles, but instead of using the left endpoint or the right endpoint touching the graph, we're going to use the midpoint of each rectangle touching the graph. Okay. And that midpoint is slightly more accurate than using our left or right endpoint. So for this first one, we are looking at the graph of x squared plus 1. Okay, so it's a parabola that has been moved up 1. And we're looking at it from 0 to 2. Okay. So we want 4 subintervals from 0 to 2. So right now I have 2 subintervals with 0, 1, and 2. So to get 4, I'm going to split each of these in half. Okay, again, my drawing's not super accurate, but we are going to attempt to get our picture. So my first rectangle is going to go from 0 to 1/2 with my midpoint touching the graph. Oops. Same thing from 1/2 to 1. Between 1 and 3/2. Oops. And between 3/2 and 2. Okay, so I do need to find where these midpoints are at. Between 0 and 1/2 is 1/4. Between 1/2 and 1 is 3/4. Between 1 and 3/2 is really 1.25. And between 3/2 and 2 is 1.75. Okay. Okay, so when we're going to find our area, these are the points, these midpoints are what we're going to use in our f of equation. So f of 1/4. Remember, our width of a rectangle is still 1/2, so delta x is still 1/2, even though the midpoint is 1/4 of the way in. F of 3/4 times 1/2. F of, what did we say, 1.25 times 1/2, and f of 1.75 times 1/2. And we can plug these f of 1/4 or whatever into our equation that they gave us. And we get a total area estimate of 2.3125. Okay. This next one, we're wanting to use a midpoint. We need 3 equal partitions to find the area under the curve. Okay. This one, we do have equal step sizes again. This table is a little bit nicer than the last one. Okay, our problem is that we want to create 3 equal partitions, and we're going to need midpoints that are given in the table. So if I create one partition that goes from 1 to 3 with 2 as a midpoint, one from 3 to 5 with 4 as a midpoint, I'll circle my midpoints, and then from 5 to 7 with 6 as my midpoint. Okay, so my area, we're going to use f of 2. The partitions are all have a delta x of 2. So that is what I'll multiply all my f of equations by. For an area approximation of 64. Okay. So midpoints are a little bit nicer than left or right endpoint, because if you notice in this example, we have a little bit of an overestimate in this rectangle, but also a little bit of an underestimate in this rectangle. And the idea is that hopefully they balance each other out. But rectangles, again, are not the only way to do this. We're also going to talk about these trapezoidal sums. And trapezoidal sums are kind of nice because trapezoids fit a little better under a curve than rectangles do. You do have to think about your trapezoids being turned. So normally we're used to seeing them kind of like this, where the bases are horizontal and the height is vertical. Here, that's not the case. The height is going to be the horizontal part and our bases are vertical. Remember, our area of a trapezoid is 1/2 b1 plus b2 times h. Okay. So we're given the same equation, same subintervals. We want 4 subintervals, so 1/2, 3/2. Now my trapezoids are going to fit really close to the curve. Okay, so I'm using straight lines to fit them. So if you were zoomed in looking really hard, it would look like kind of like that. But see how it's getting nicer to or closer to a smooth, nice curve like we want. Okay. So when I go to do my area approximation formula, my first trapezoid goes from 0 to 1/2. So I'm using both of those endpoints, dividing by 2, and the height is that delta x, which is 1/2. Okay. My second rectangle, or not rectangle, sorry, trapezoid, goes from 1/2 to 1. My third trapezoid goes from 1 to f of 3/2. And then I need to fit a fourth trapezoid in here somewhere that goes from 3/2 to 2. Okay. So my area, and I'm plugging these f's into my original equation. F of 0 would be 1. F of 1/2 would be 1.25. And essentially, I have this over 2 and I'm multiplying by 1/2, so that's the same as dividing by 4, okay, because those denominators multiply. we get an area approximation of 4.75. Okay, and as we compare that to our midpoint one, our midpoint estimate was 2.3, this is 4.75. We are a lot closer to what that actual area is, okay? And we'll look at how to find that actual area here in a little bit using integrals. The last part of midpoint and trapezoidal, we're going to do this trapezoid of this particle given this table. We know that the initial velocity of our particle at v of 0 is 3. We want to find the velocity at time 8. Remember, acceleration is the derivative of velocity. So if we take the integral of acceleration by using a trapezoidal estimate, we're going to end up with our velocity. So we're looking for velocity of 8. We're going to use our trapezoid. So we're going to have a of 0 plus a of 2 over 2. The width between these is 2. Then we'll have a of 2 plus a of 5. Our width between those is 3. A of 5 plus a of 7. Our width there is 2. And then a of 7 plus a of 8 with a width of 1. Notice they give us this initial condition that when velocity is 0, or time is 0, velocity is 3. So we're going to add on our plus c like we would do for integrals. Okay. And that way we can find it a little bit more exacting than the approximations we're used to. So we're going to plug in numbers from our chart. A of 0 is 0. A of 2 is 4 over 2 times 2, which will cancel. 4 plus 13 over 2 times 3. 13 times 21, I'm sorry, plus 21 over 2 times 2. 21 plus 23 over 2 times 1, and then plus c at the end. So we get the velocity, if we add all these parts out, is going to be 85.5 plus c. We are given an initial condition that when v of t is 0, velocity is 3. That is like our y-intercept, right? So that would be c. So our velocity at 8 is approximately 88.5. Okay. If you flip to the next page, page 159, 160, that is your homework tonight. Okay, it goes over all of Reimann sums, left, right, midpoint, trapezoidal, and gives you some practice with that. I'm going to move along to our next part of 5.3, which is definite integrals. This is what your quiz is over next time. Okay, so definite integrals basically says, can you do an antiderivative or an indefinite integral like we did in 5.1? And then can you use your limits of integration to find the area under a curve? So we're given a little bit more specificity. Is that the word? With finding our area. So you're used to seeing this integral without these a and b here. That was an indefinite integral. Now we're seeing those a and b. Those give us a closed interval, which are, closed interval, which our integral is continuous over. So we can find the definite area, okay? The definite integral works from left to right, okay? Going from our least values to our most values. So A should be less than B. If for some reason we have B to A, so working right to left, then we are moving backwards. And our integral will be negative. So that's what we're seeing down here. So instead of B to A, we can write it as negative from A to B. If we're putting numbers with it, instead of going from 4 backwards to 1, we'll go a negative interval from 1 to 4. Okay. So far in math, you have learned that area is always positive. That is no longer true. Area above the x-axis is going to be positive. It is below the x-axis, it is negative. Okay. That also means that if we're moving right to left, that backwards direction, that negative area, we had a negative area, so under the x-axis, because it's moving backwards, it would be counted as positive. So we're going to play around with this a little bit with this graph. Okay, so we're told what the area under these curves is, and we just want to make sure we can kind of figure that out based on our limits of integration. So if I'm going from 0 to 1, that's this area right in here under this curve. We see that it has an area of 2. Okay. If we're going from 0 to 4, we're taking this area of 2 plus this area of 6 for a total area of 8. If we're going from 1 to 6, we're getting this area of 6 in here, but then this area of 3 is under the axis. So we're going to subtract it off for a total area of 3. If we're going from 4 to 8, so here's 4 all the way to 8, we start out with a negative area of 3. We add a positive area of 7 for a total of 4. So this to this. All the way from 0 to 8, we have 2 plus 6 minus 3 under the axis plus 7 above. Total area of 12. And then what if we went backwards from 4 to 1? So here's 4, here's 1. We put a negative in front of that integral and go from 1 to 4. So instead of positive 6, our area is negative 6. Okay. We're going to skip this little piece at the bottom, not important. But we do want to talk about the properties of the definite integral. So if x is defined to a, and we move from a to a, meaning we have not moved any area at all, we can't have any area, so it must be 0. If f is integratable, over the entire interval from a to b, and c is in between a to b, then we can do something that breaks up our integral. So we can go from a to c, take that area, and then go from c to b. So that's kind of what we did here. From like 1 to 6, or even from 0 to 4, we went from 0 to 1, stopped, took that area, and then went from 1 to 4, took that area of 6, added them together and got 8. Or if it was below the x-axis, like in the next one, we subtracted. So that's what property 2 is illustrating. Property 3, we kind of talked about last time. We can take a constant k outside of the integral. We also talked about 4 last time. If we have 2 functions, that means we can take the integral of them one at a time. So we remember we broke up polynomials and took the integral of each piece. Same thing can happen when we have limits of integration. When we have an even function, if we're going from negative a to positive a, then we really have 2 times our integral from 0 to a of f of x dx. However, if it is odd, then we have an area of 0. Okay, and if we think about this, think about a parabola as an even function. So I'm going from negative a to positive a. Instead of integrating this whole region, I could go from 0 to a, so just this piece. And I have, should be technically the area under the curve, but bear with me. We have 2 times that area, okay? But a cubic function is odd. So this area will cancel out with that area, okay? So those are what those are illustrating. If I could draw a little better. Okay, so let's look at some examples that we can look at using our definite integrals. Okay, and these are the last 2 examples. So I totally lied. There is not a quiz next class. We need some more practice with definite integrals. So we will not do that next class. We will do that probably after we have some more practice. So no quiz next class. But if we are looking at these last 2 examples, we are given that the area from 2 to 4 of f of x is 5. The area from 2 to 6 of f of x is negative 6. We want to find the area between 4 and 6. So if we're thinking about this, 2 to 6 is our biggest space, okay? That's the biggest interval between a and b for any of these. Okay, so I'm going to let that equal the area between 2 and 4 plus 4 to 6. Okay, so this is that kind of idea of breaking up my integral from a to c and then from c to b. And it works really well for this one because I know this value is negative 6, this value is 5. What I don't know is this one. This is what I was wanting to find. Okay, well now we've kind of have it as the only integral left. We can isolate it, so leave it on a side by itself, and we see that its area from 4 to 6 is negative 11. Okay. Down here, we're given the integral from 1 to 3 of x squared is 26 over 3. Integral of x from 1 to 3 is 4. Integral of really just 1 dx, okay, there's an understood 1 in there, from 1 to 3 is 2. and we're asked to evaluate this, okay? So I know what x squared, the integral of that is. I know what the integral of x is. I know what the integral of 1 is. So I can take and break this into separate integrals. Okay. Oops. And then I can move any constants outside the integral. Okay, so this uses properties 3 and 4. So the property 4 in this step and property 3 in this step. Well, now I know how to evaluate this. This is 26 over 3. Don't forget you have that negative outside the integral. We know the integral of x from 1 to 3 is 4. And we know the integral of dx from 1 to 3 is 2. So we have negative 26 thirds plus 16 minus 6, which gives us 4 thirds. Okay, notice in neither of these problems I used a plus c. That is because they are definite integrals. I no longer have to use a plus c. I know where to evaluate it over. I'm just practicing using my properties. So no quiz next class. And remember, your homework is in your notebook, page 159, 160. Okay, and I will see you next time.